Testing, testing. Okay, you can hear it now? Okay, perfect.
Okay, are we ready? All right, 3, 2, 1, vote. All right, I'm seeing ones, fours, fives, threes, twos. Oh, I'm seeing them all. How fun. And the answer is little green men. So we didn't know what they were, so it was fun to think maybe they are aliens, little green men out there sending signals throughout space. Question number 2. This is a visualization of what happens when a cosmic ray hits the Earth's atmosphere. What is this effect called? All right, I see somebody ready, so let's vote. 3, 2, 1, vote. I'm seeing fours, five, twos. I see a 1. I see a 3. All right, once again, I think we've got the whole choices, so let's see what it is. It's an air shower. So you can kind of see it. It's like you're standing under the shower head, except for water, you're getting showered with energetic particles, which is less ideal, harder way to get clean. All right, question 3. The first animal or animals to travel in a hot air balloon. Okay, this time if you're picking more than one, you can flash through the answers you're choosing. 3, 2, 1, votes. All right, I'm seeing ones, I'm seeing twos, I'm seeing some flashing, 3, 4s, 5s. Let's see what the answer is. Wow, that one had a big reaction. We're all thinking about a sheep, a rooster, and a duck riding together in a hot air balloon. And that was in 1783. So hundreds of years ago, testing out this technology, probably to see if it was safe, checked it on some animals first. All right, there are no animals in balloons that are used for cosmic ray science. They go up way too high for animals to enjoy or to be able to breathe well. So, question 4. Astrophysical jets occur when materials are expelled from astronomical objects at high energies, like black holes. How long are these jets? I'm hearing lots of good discussion. Collaboration is how science happens, so love to hear it. Let's vote in 3, 2, 1. All right, I'm seeing 2s, 3s, 4s, 1s. Do I see any? Oh, and a 5. All right, we've got them all. And here, let's see. The signal's not going through Matthew. Oh, there we go. The length of a galaxy cluster. So this is tens of millions of light years. So this is really, really big. It would take light leaving here tens of millions of years to travel all the way there. So that tells you how zoomed out this artist's rendition is, because these are huge, huge objects. All right. Our last question. The Amaterasu particle is one of the most energetic particles ever to be detected. If all of the energy of this particle were to be transferred to you directly, what would it feel like? Hopefully, the only ones that you have ever experienced is the light breeze. Okay, let's vote. 3, 2, 1. I'm seeing 1s, 5s, 4s, 2s. Do I see any 3s? Yep, I see some 3s. And the correct answer is being hit by a brick. So that maybe doesn't feel very dramatic. A brick is something that humans can pick up and throw, hopefully not at each other, but you could. But think, a particle is so small, you would not be able to see it with your eyes. You wouldn't be able to see it with a magnifying glass. You wouldn't be able to see it with a visible light microscope. So something that is so, so small can pack a really big punch. All right, moving on to announcements. Our next talk is May 1st. We're going to start it at 7:30. So now that we're entering the summer, the sun is setting later, so it's still a little bit light out, darker. We are hopeful that the weather will be good, so we want the skies to be dark enough for us to see. So our next talk, May 1st, in this room at 7:30, will be with a graduate student, Ryan Golens. And we will have a summer series. We just will announce it in June. So stay tuned for our summer series as well. We'll hopefully also have good observing then too.
So today I'm going to talk about an outstanding problem in physics that's been around for about 100 years. And I believe
bit of a signal as you're moving up this tower, but we need a lot more height. So why not take it to the skies? And this is exactly what Victor Hess did. So the early kind of experiments here were taking one of these electroscopes up into a hot air balloon. And what you'd expect to see is that as you move kind of further up, these plates will kind of move together faster if you're moving towards the kind of form of radiation. And so for several balloon flights, including one in a solar eclipse, they were tested. And here you can see roughly what he was seeing. So this is just as he's kind of moving up in the air here, altitude, and this is roughly the amount of radiation. And so as he moved up all the way to 8 kilometers, what he saw was in the beginning, things were kind of not really moving that much, but as he got up and up, eventually it revealed that we were seeing something from above. That part of this radiation that's affecting us here on the ground is coming from space. So Millikan, who actually ends up being a professor at Columbia, coins the term for this radiation, cosmic rays. And he repeats several of these balloon flights and confirms these results, shows that they're robust, and now we've got a problem on our hands. We've got two things. We've got radiation, which at the time we don't even know what this is. And it's coming from space, but we're in space. So the first problem was the first one to kind of be solved. And it got solved with experiments like this one. This is a cloud chamber. And what cloud chambers do is suspend alcohol just above the point where it will form clouds and condense. So any... Sorry, just a second, folks. So what you're seeing here is alcohol suspended just before the point of cloud formation. And so every time a charged particle passes through this, this chamber, it forms a cloud behind it. And the properties and structure of that cloud actually tell us what type of particle, what its mass is, and what its charge is. And so we're able to see, just by looking visually by eye, as people were doing in the early days, several different types of classes of strips. You can see these big fat ones that appear. These are these alpha particles, which we now know are kind of heavier nuclei. But we also have these kind of long strips of protons, as well as several kind of electrons and muons. And all of these fundamental particles, at the time we didn't know the whole classes and stuff, but we were starting to kind of give them these original names that ended up coming through observations like this. And we didn't have really these strong particle accelerators that we have today. And so one of the best accelerators that we had, or these places to supply particles to us, was these particles from space. So a lot of these original kind of particle experiments were taking place up top of mountains in order to get closer to these cosmic rays, which at the time were the best places to study particle physics. So what we know about them now is that they're about, the ones right before they hit the atmosphere are about 90% protons. So most of what we're seeing, and when we're talking about cosmic rays, we're talking about protons. Quantities. So whenever I talk about cosmic rays, you can think about these just generally as charged particles from space, but more specifically, most of them are going to be protons. And when you look at the amount of them is actually quite remarkable. So this is just showing how much particles there are raining down on Earth of us, depending on how energetic those particles are. So when you look up here where the data starts to kind of cut out because the experiments are not coming, we're getting about 1 per second per meter. So these are basically passing through you kind of at all times, and kind of subparticles from these, and even more from kind of resultant secondary showers, and this continues upwards. So these are passing through by hundreds. As you get to kind of the tippy tip, though, of what we've actually measured, the rates start to get much, much lower. So the most extreme of these events, we're seeing only 1 per kilometer squared per century. So if you want to wait and build an experiment to catch those, that's fine. You could build one that's 1 kilometer squared. You have to wait 100 years. So what we do is we build ones that are tens or even hundreds of kind of kilometers squared in order to catch this very slow tail of these cosmic rays, because you can see all of these little kind of purple points are all individual measurements by people over the last 100 years to measure at each one of these energies how many particles are coming down. And so although, this looks kind of almost featureless, there's actually a couple little kind of bumps and dips that interest us quite a bit. But for the time that I'm going to be thinking about, I'm talking about just this kind of little range. We know that they're kind of probably protons and mostly 90%, and we know kind of roughly how many there are. If you want to know kind of that answer to the question of where they're actually coming from, you might say this is a very simple problem, Matt. Just tell your detector to tell you where that particle came from. Instead, you get something that looks kind of like this. And so this is roughly kind of in terms of brightness color. This is the whole sky unfolded. And basically, there's a little bit more coming from over here and a little bit less coming from over here, but they're coming from everywhere. And there's not really any clear point where you would say, okay, this is like a star, or this is something where I can say all of these ones are coming from. Maybe there's some more over here, but there's kind of not really kind of this clear structure. And the reason for this is because what you're seeing, those two big blobs, are not actually caused by really dominated by the origin of where they're coming from, but because those particles are charged, because they're mostly protons, they don't actually get back to us and point with the same direction that they came from. So say you had some cosmic ray source, something out here was producing cosmic rays that were going to be eventually measured at Earth. Well, the track that they do is constantly deflected by the magnetic field in our galaxy before arriving. So by the time these little protons end up hitting the Earth, they don't point back in the direction from whence they came. They're just showing us the magnetic field structure of our galaxy. It would be great if we had something that was produced in the same object and came directly for us, and luckily we do.
Bad luck all around.
I apologize. Okay. Okay, can people still hear me? Okay, I think we should be good. Okay? Wonderful. So, going back to our story, so protons aren't useful directionally. They're hitting us all the time. They're giving us the energies. They tell us that there's something out there producing them because we see them. They're energetic. They hit us. There's something out there. But they don't tell us from where that thing actually is. Luckily, what we do have are photons, particles of light. And these particles just are light, and they point directly back and aren't deflected in these strong magnetic fields. And it's in fact a property of a lot of the production of these protons that when you actually are making these and accelerating them, almost an inevitable product is photons that have roughly the similar energy, about a tenth. And so what you want to look for is gamma rays, or kind of photons with matching energies to those actually protons that we're seeing. And so why do I say gamma rays? Why do I say that? And so this is just because of all of the different kind of structure of light. This is what's known as the electromagnetic spectrum. And you can see here all of the light that we see falls in this really tiny value range of different wavelengths or energies or frequencies. This tiny little range is all that we see. As we kind of move to less energetic forms of light, lower energy light, we move into this IR, which is the infrared, and radio, which is all just photons. And as you get to kind of more energetic light, you get into the UVs, eventually you get into the X-rays, so this starts to be kind of what original people were calling that radiation, and then eventually you get to gamma rays, one of the most energetic forms of light. And everything beyond a certain energy we call a gamma ray. And so what you're looking for is really gamma rays with the energies of those same protons And if you see this, if you see a gamma ray source, it will also almost inevitably be a cosmic ray source. And so what does the sky look like in all these different wavelength bands? And I think it's important to just stress that we only see with this, but the sky looks dramatically different. So I'm going to highlight an object. And so this is a very famous object. This is called the Crab Nebula. It's a supernova remnant. So what's left over when a star dies? This star actually died in 1054. We have written records of people actually seeing the light from the star during the day when it went off. And so this was a star originally called a guest star at the time, and as it exploded in 1054, it slowly starts to expand outwards in a blast wave. And what you're seeing here is a green colored version of all of the optical light. So the structures you'd see here would be similar to the structures you'd see with your own eye if you look through even a small telescope. You can see some of this, but not to quite the detail that the space-based instruments can. But if you change which wavelength you're looking at, if you said look at the IR, it looks slightly different. Some of the structures are highlighted more. It's a little blurrier just because of the resolution, the type of quality of instrument. But it looks dramatically different when you start to look at the kind of radiation coming from these systems. And the first kind of picture is X-ray. So this is the exact same object. And now all of that kind of expanding outwards cloud shell is really kind of subdominant to what you're seeing in the central kind of component here. And if I increase the clarity of the image by looking at it with a higher angular resolution X-ray telescope, you get a picture of something that looks like this. And now you can see that this kind of complicated object of this expanding blast wave you see is being powered by this small little central engine. And this small little central engine is left over when massive stars die. It's a compact object. So the core of one of these massive stars, after it dies, is compressed and has the density roughly of kind of the nucleus of an atom, but spread over the size of roughly the island of Manhattan, roughly 10 kilometers. These are extremely dramatic objects. And even more kind of intriguingly, these objects are spinning, and they're spinning fast. So you might know of when figure skaters in the Olympics start to do their kind of spins, they move their arms in and they spin more rapidly and more rapidly. As stars begin to collapse, a similar process happens. Via conservation of angular momentum, you rapidly start spinning this core of this massive star. So remember, roughly the mass of even our entire sun compressed into the island of Manhattan. A single teaspoon of this material would weigh as much as all the humans on Earth combined. It's an extremely dense material. And you might have heard other talks from other speakers kind of earlier who are talking and studying exclusively what this material structure actually is. And so this sits at the core of this kind of larger expanded shell, which is only really revealed, recall again, when you look at this with these different colors of light. Now, the question I had, remember, was how much energy is this thing actually able to put out? Is it able to accelerate not just kind of low energy protons, small energy, is it able to get up to those energies that we're seeing, those remarkable energies all the way up, more powerful than anything that we've actually been able to produce on Earth? And the key to finding that is gamma rays. And when I look at the gamma ray picture, you know, everyone get really excited. It looks like this. Now, okay, it's just a blob, but gamma ray telescopes don't quite have the resolution of the X-ray telescope, so they have to work in tandem with one another. So the gamma rays, even seeing anything from this region, tells you this is one of the most energetic places in the galaxy, but it doesn't really tell me it's important that we don't just have one instrument, we have an entire suite that covers all of these different multi-wavelength domains and do what we call multi-wavelength astronomy. Now, looking here, this is what the sky looks like in optical light. So this is the entire sky. You can see several structures. The middle plane here you see is the plane of our own Milky Way, along with its little satellite galaxies. And this is the center of the Milky Way. And you can see these kind of dust clouds causing absorption, and the light that you're seeing is mostly from stars. But when we look in the X-rays, this is the picture that we see. So this is coming from the E Rosita X-ray telescope. And what you can notice is, and I should also preface this as if it wasn't clear, all the images in the higher energy bands are all going to be false color images. Of course, we're adding in the image kind of, the light to our own eyes is actually invisible. And so when you're looking at all these little structures here, you can now see that many things pop up. This blob, which was kind of almost innocuous in the other picture, now becomes a place that you might want to look at to see if there's gamma ray emission. And now, everyone get excited again. I'm going to show you the gamma ray picture. Okay, it's a little blobby, but it's still really important. And it's also got holes. And I know, this is why it's important to build a gamma ray telescope in the southern hemisphere so that we can actually see what's going on here. Right now, we're completely blind. But that still plane of the galaxy is still seen here. And there's several sources which are extremely bright in the gamma rays. And so all of these things that you're seeing here are all of these potential sites of cosmic ray production. And really, this kind of picture of the sky at these energies was only available to us in the last couple of years. Okay? So even though it might not look like much, it's a pretty important for gamma ray astronomers like us. The maps that you see and how we actually do this work, because this is the work that I do. I'm an observational astrophysicist. What I do is actually try and measure these gamma rays. Okay? So when these gamma rays are traveling to Earth, remember you have all of these cosmic rays that are propagating in kind of all these other directions, being deflected by those magnetic fields. The gamma rays will come all the way up to our Earth's atmosphere. When they come to our Earth's atmosphere, luckily we have produce antimatter. You might have heard of antimatter. You might not know where it's found, but it's found actually ubiquitously in nature, in the atmosphere, and it's produced when you actually have these high energy cosmic rays coming through that are capable of producing an electron and positron pair. Now, this is a reaction that happens spontaneously when you get to enough energy. And so you can see that as these kind of things were coming down, it split off into these electron positrons, and as they continue to move, you get more and more of these electron positrons. And all of these particles are traveling through the atmosphere, and you're getting more and more of them in this kind of chain reaction that's producing that particle air shower. And this particle air shower that we're seeing raining down is doing something in the background. All of these particles are traveling faster than the speed of light in air. So you might have heard that there's an absolute limit to the speed of light, but that's not true in a medium. So like in water or in air, things can actually travel faster than the speed of light in that medium. And so when you're having particles that are this energetic traveling through the atmosphere, what they're actually producing is a blue flash as they go. You produce this kind of radiation called Cherenkov radiation, which is basically blue light. And so these particle air showers, along with the particles that are raining down, come with this pancake of blue light. Very, 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 very minute. And the way that we kind of measure these is through just optical telescopes, large dish optical telescopes. These pancakes come down, and as they go kind of over a series of telescopes, the blue light will bounce off of the mirrors that are kind of flashes. These really, really narrow kind of second flashes are then recorded for each shower. And we don't have a single telescope doing this. Current generation arrays have 4 telescopes that all image that same flash of light, but the next generation are going to have up to 30. And what that allows us to do is look at that single kind of particle from various directions, which allows us to tell the type of particle, the energy of that particle, and where that particle is coming from. And so for gamma rays, that's extremely important, but it's also important to know that you're looking at a gamma ray versus a particle air shower coming from a charged particle. Now, we've got a lot of these telescopes spread throughout the world. The one I work on is up here, which is located in Tucson, Arizona. This is the Veritas telescope array, but there's telescopes scattered throughout. There's several in La Palma in the Canary Islands, several in kind of Namibia, and then kind of wide-scale detectors which look a little bit different, kind of coming from a couple in China and down south. And so the Veritas array is this one. So this is a real kind of video of the telescope that I work on. And so the size of these mirrors for context are 12 meters across. These are some of the largest telescopes actually in the world. And we don't have a single one on site. We actually have several. So you can see one down here, another one kind of over here, and another one back here. And so those multiple telescopes Now, this little box is filled with 499 of these guys. These are little cameras that actually flash at that kind of really rapid response. So your typical camera, might open for a kind of 1/10, 1/100th of a second. We need to be looking at kind of more rapid flashes, kind of 1/100,000th of a second, and even faster. And so each one of these little kind of devices costs around $500. We implement each one of these with kind of 499 of them, so you can do the math. And they do break, so you might want to add in a couple, and which is why I'm allowed to swing one around here. And so the kind of overall picture here of these kind of little rapid devices is to power these kind of large-scale telescopes. And there's going to be a little person there that gives you, again, the context of the height of these arrays. Now, typically, I go down for about kind of 2 months in these arrays, and the whole array kind of system is operated by a mixture of researchers, active researchers at universities like Columbia, and a collaboration of people coming from Ireland, Germany, and several other countries, including Canada. And so now we have kind of this kind of rough picture. We've got the telescopes that can actually image these gamma rays, like Veritas. Roughly, we've seen kind of why gamma rays might be important, because they trace back to those high energy particles. We can start to look and see what these telescopes actually see. And so because these are telescopes, you have to point them somewhere, so you have to have a guess. You have to come up with a couple clever thoughts on where you might think that these sites are. We don't know, but we're guessing, right? Informed guess. And the rough ideas that we have are you kind of want a site to get these particles to these energies that's either really, really big or really, really strong. But if the hill is super, super long, it can have a very narrow slope and still accelerate things to these high energies. And so we often think these things are accelerating magnetic fields because they're charged, so the strength of that magnetic field is roughly the steepness of the hill, and the size of the accelerator is roughly kind of the length of it. And we could draw a line across here that says anything that falls above this line is able to accelerate the kind of tip of that cosmic ray particles, and anything below it is likely not energetic enough. And we can populate this with a lot of sort of objects that we know of. So down here is actually the Large Hadron Collider. So you can see that's roughly kind of a kilometer, gets about a Tesla magnet. Up above that are those compact dead stars, the cores of kind of exploded stars, these neutron stars or pulsars. These are kind of stronger magnetic fields, but roughly kind of the same size. We then have sunspots, which are not quite there. They don't have really strong magnetic fields, and they're not really that big. Same thing with the kind of distance between planets. Maybe the magnetic field there is quite weak, but the planets are quite far away. Still doesn't quite cut it. The things that do cut it are these guys up here. So these are the actual kind of not the pulsars themselves only, but also the kind of area around them are these rich magnetic field environments that last quite once. So the blast wave, kind of these particles might be carried by this actual blast wave. And then stuff like kind of blazars, which I'll talk about in just a second, but the galactic disk as well. Here, it might just be that the particles are traveling through our galaxy, slowly building up energy. But I'm going to focus on these little guys down here, which are called microquasars. And so microquasars are some of the most interesting objects in the galaxy. And so here is roughly what one looks like. And so you can see, like those supernovas, there's this big blown out shell kind of around them. But when you look inside, it's not now just this collapsed core of a star. Instead, what you have is called that neutron star again. And then it's being driven by power coming from a large star. And what it does is drive this large outflow as it kind of spins around. So this is all an artist rendition, but this is what it actually looks like when you take a photo here of the kind of inner core of one of these systems. You can see actually by eye these kind of helical structures which are driving this kind of large-scale model that we have. And each one of this is roughly kind of being measured in this unit, which you might not have heard of, which is called a parsec. 1 parsec is the distance basically to our nearest star. So you can think of this as the kind of distance between stars. Roughly kind of the time light takes to travel kind of several years. So now we can zoom out. And so this is the little core. But what it actually is driving kind of outwards are large extended structures that fill up that kind of blown out shell. And so this little tiny engine that we have there, which is that big massive star feeding onto this little black hole, is actually driving all the way out to here, where we have these kind of big, huge structures that appear out of almost nowhere. And now we're not exactly sure what causes these structures, but we see them quite clearly, and we see them on both sides. And you can see roughly the distance there. It's about 100 times the kind of distances between stars. And you can see this is what the whole thing looks like. So right out here in the red, you're seeing what comes from if you take a radio picture of the object. And then these little X-ray ones, the same way that the X-ray was revealing where the kind of central engines were, they're showing you, okay, these might be places that are quite interesting to look at. And so this is an artist rendition again, but if you actually look at the data, I think it's no less remarkable. So this is the X-ray picture. And you can see here, there's still that little kind of black hole system in the little middle. And then it's powering these kind of large, extended, blown out kind of structures that we really still don't fully understand. We think that there's something to do with material hitting something, but the exact structures and the exact dynamics are still a question up for debate. But remember, the same thing we did with the pulsars, we're going to do here again. We're going to ask ourselves, okay, this is a nice structure. We can see all this X-ray detail. We can see these engines, but does it emit gamma rays? Is it one of those objects that we're seeing in that big map? Is it something that Veritas, a telescope on the ground, can see? And so we stared at this thing for about 20 years, and we slowly built up one gamma ray at a time, all the way until we had about kind of several hundred gamma rays. So not a lot, but it was a kind of detailed effort that took a long time. And now I'm going to show you the picture. And so, you ready? There you go. And not super exciting again, a little bit blobby, but you know, it took about 20 years. So, yeah. And other telescopes were not leaving us kind of to take our time. A couple of years kind of before we came out with our results, there was another group that also did a very similar study and also found these kind of large extended structures in the gamma rays. And so all of us kind of across the world are now in roughly agreement that we're seeing these kind of large extended gamma ray structures, which is telling us that these microquasars, these incredible little systems, are capable of being some of the most energetic places in our galaxy and capable of producing those cosmic rays. And so both of these kind of pictures we really didn't know until about a year ago. Okay. Now, finally, I want to get to stuff that we kind of don't even know about now, and what are the still kind of open questions. So just to kind of reiterate again, because maybe some people got a little bit lost at this point. So what's happening here is we have this kind of big star. It's being fed onto this little kind of tiny black hole here. And the black holes, where these came from, it doesn't really matter for this case, but we think that they came from the kind of collapse of a massive star. So some of them end up as these kind of compact cores that are pulsars, but some of them end up as little tiny black holes. And these little black holes are ripping apart the kind of stars that are nearby them. And they're driving these kind of large outflows. But this process is really chaotic and not very regular and very random. So when you actually look at the brightness of the gamma rays over time, it's not a constant flat line. In fact, it bubbles kind of up and down and up and down and up and down. And so what you see here, each one of these downward arrows means we didn't see it. So we looked, we didn't see it. And you might notice the dates here. This is from kind of the last couple months. And so what you're seeing is us continuing to look at it, but then, oh, we got lucky. And here are these kind of couple observations building to just kind of the past week, which is why I've not been able to get too much sleep, because it started to bubble up again. And so every time the gamma rays see something, everyone else begins to point at it as well, and we trigger these kind of large multi-wavelength campaigns to get that coherent picture on those pictures from all those kind of different wavelength bands. And so you're sitting kind of right now in the middle of one of these kind of exciting gamma ray moments. And if you want to go out and see this thing, you can actually, but not with your eyes because it's all producing gamma rays, but you can see the region of the sky that it sits in. And this is where I'm going to kind of leave us because we're still answering questions about this thing because we still don't know a lot about it. What really causes those kind of knots and structures to form? How do the cosmic rays actually end up in these systems? We know that they might be produced in these systems, but what exact mechanism gets them up to those energies is still an open question. And we also still don't really know how they get in Antarctica today. But if you want to see this guy's called Cygnus X3, the one that's bubbling up right now. And you can find him in the Cygnus constellation of the Swan. And the only downside to this is you can see him perfectly from New York City because he sits right in the triangle between some of the brightest stars in the sky, Vega, Deneb, and Altair. But the downside is that those stars are only really up after 2 a.m. right now. And so you can wake up at 5 a.m. and maybe see it if you would like. And the kind of little region here where this kind of microquasar sits is this extremely kind of complicated cloudy region here. So if you have a big telescope, you can take kind of images of some of these clouds, but the actual microquasar is quite well hidden. And this is kind of where we sit right now. We've got these little systems. We know kind of where they're sitting in the galaxy. We know they're capable of producing gamma rays, which means likely they're able to produce these cosmic rays as well. But all these kind of open questions about their structure, formation, and all the details are what we're still trying to figure out to this day. The last thing I'll say is that all of that has to do with our galaxy. There's a completely different group than me who's working on more powerful objects. These little black holes and these little microquasars, you might wonder why they have that name. Why micro, why quasar? They're some of the most powerful places in our galaxy. Well, the name microquasar actually comes from this idea of having a quasi-stellar object, because when people were looking up at very, very far and distant things, they were seeing things that looked kind of like stars, but a little bit weird. And so they called these things kind of quasars. And the small versions of quasars, which we now know are the kind of powerful energetic cores of those large kind of galaxy-sized astrophysical jets, maybe accelerating particles much, much greater than anything we have. Are much less massive, and they power kind of less extreme environments, but still the most extreme environments that we have in our own system. So I'd like to kind of summarize the last kind of couple thoughts here. So cosmic rays were discovered through a very simple kind of electromagnetism experiments that you can do on your own desktop. You can download an app on your phone today and actually detect cosmic rays yourself with your phone camera. We can see in our daily life. And those questions brought us up in balloons and all the way to kind of some of these most extreme and weird environments. And I didn't even get time to talk about some of the other things that I love, like stellar explosions in more detail, and even kind of weirder objects than the ones that are proposed here, like dark matter. But the kind of questions that we're kind of building towards was gamma rays are the key to unlocking these little environments. And just because of the instruments that we were able to build within the last 20 years, we've been able to put together a picture, and microquasars now are some of the most promising candidates for the production of sites of these cosmic rays. And there's still a lot of questions about microquasars, and I'm going to be really excited to try and answer those over the next kind of 5 to 10 years. And thank you. Okay. So the question is, if air showers are propagating faster than the speed of light, do you see them before they hit the atmosphere? Is that correct? And so what's happening with the air shower is that the light that's being produced as that initial particle kind of hits is all traveling with it. So the particle hits it at one time, and as this kind of thing is propagating downwards, it's all traveling at the absolute kind of near the absolute speed of light. It's not traveling faster than the absolute speed of light. That's a kind of cosmic no-go, right? But as these kind of all particles are traveling together, the light that we see all comes in this kind of big, large cascade, all at that exact kind of same time. And that kind of little narrow window there is why it's hard to detect. Does that make sense? Maybe it's just to say that we do see it after it's hit the atmosphere, but that's a remarkably fast process because it's traveling very close to that speed of light. So that's a great question. And so the original discovery of microquasars goes back about 50 years. And so what people were originally seeing were just these large-scale X-ray patches. So at the time when people were looking at these things, the X-ray pictures looked like the gamma ray pictures. So they were these big blobs on the sky that we didn't really know what they looked like. We couldn't see anything very clearly. And these big blobs, eventually, as we build better and better telescopes, get clearer and clearer. And we can figure out what's actually going on. And so it's like if you were looking at everything kind of through a very blurry kind of, like on a cloudy, foggy day or something. That was when people were originally seeing these things. When we actually figured out what they were was a slow process that years ago. Yeah, so the question is a really good question. And the question is about whether or not when you have an air shower, you get electrons and positrons, matter and antimatter. And it's exactly right that the reason we get this is because of what Einstein said, E equals mc squared. And so when you get a particle that has sufficient energy, sufficient E, it's very easy, no matter what that particle is, it could be light, it could be anything, to produce particles more mass, the m on the other side. And the c is the speed of light squared. And so when you're getting these multiple kind of particles that are being produced, you do get kind of an equal amount of positive and negative, or matter and antimatter. And when matter and antimatter collide, you do get what's called particle annihilation, which does produce energy again. But because of the way that these things are propagating and the energies in these reactions, it actually ends up that these particles split far enough away that you don't get this just where they turn back immediately into a photon. So it's about how the kind of trajectories of these things end up moving, that if they have sufficient kind of energy going in, they won't just merge back in immediately. So it doesn't even need to be vacuum. It could just be space, right? Just enough room, right? And so these particles, the antimatter and the matter, kind of come crashing through and they spread out. And you get both of them actually do end up producing more light through kind of more complicated processes later on. It's actually a kind of fancy German word. So what happens is as these particles are being slowed down by the atmosphere, because just the kind of electrical charge of all the kind of atmospheric particles slowly slows down this kind of electron moving through. So it's getting slower and slower and slower and losing energy. And that process of losing energy, that process of breaking, releases photons, these kind of lower energy photons. And that's called breaking radiation. But we call it the German version because it was the Germans who originally kind of wrote this whole thing up. And so it's called Bremsstrahlung radiation. So that's breaking radiation. And so you do end up getting more light from these air showers, but it comes in kind of through different processes than just annihilation. So eventually you'll get kind of later interactions. Yeah. Kind of question, maybe I'll start. So the question was, can we capture this energy from cosmic rays and use it as a power source? Now, the energy that cosmic rays give you, this is a problem for kind of two reasons. One, it's an extremely inconvenient way that it's actually giving you this energy. You like giving a small amount of energy at kind of lower energies and a lot of that happening at the kind of same time. So having your things come as really rapid particles, it's actually really hard to stop and capture the full energy of those particles. So supplying energy and kind of giving energy in the form of really energetic particles is really inefficient. But the other problem that you have is that even though there's a lot of cosmic rays coming at all times, the relative energy density that you're getting from cosmic rays is much lower than you get from other processes. So you can just look at the sun, and the radiation that you're getting from the sun is probably a much more efficient way of actually supplying that power. And so there's much more better ways of doing it. There's nothing problem with, in theory, capturing some of this energy, but it's just not very much. Yeah, so the question was, when people saw light in 1054, so let me actually just, I'll go back to the question slide in a second, but I'll show back this kind of stellar explosion here. Okay, so the question was, when people were actually seeing this light in 1054 from this supernova remnant from the crab, what were they actually seeing? And so, and how are they seeing it, and how do they know what they were looking at? And that's a great question. And the answer was, one, they didn't know what they were looking at. So at the time, a lot of these kind of original things that were being seen were called various things by the various different cultures that were measuring them. In China, these were called guest stars. So what they looked like, if you were standing on the ground and looked up in the sky, is imagine that you were looking at all the stars and constellations that you knew, and then all of a sudden one day there was a new star there, a star that wasn't there the night before. And that star was getting brighter and then slowly getting fainter over time of kind of a couple of weeks. That's what one of these things would look like. And so you'd have this kind of new star, guest star, or the kind of, from the Latin, where we get this idea of nova, new star, right? And the word supernova, which you might have heard, is one of these super kind of bright versions of these new stars. And that's what they're seeing. But how did they figure that out? It wasn't until much, much later, kind of almost 1,000 years later, where we started to piece together some of these pictures of what's actually going on in these systems. And we did that using the powerful telescopes that we have today to take pictures like this one, which show what's actually happening. So there's two things so the answer might surprise you. The first problem with the air showers is that you can't, if you could see all the air showers that we detect with an instrument like Veritas, you would walk outside every minute. Veritas detects about 300 showers per second. So you could look up in the sky, and everywhere, basically everywhere in the sky, you'd see flashes of blue light. And the flashes of that blue light, for the time that that pancake hits you, are the brightest things that you can see. But the problem is just how narrow in time those flashes are. So because your eye is not sensitive to these very, very, very narrow flashes of blue light, you don't end up actually perceiving anything. That's happening all the time. But people might be following something that's coming down right now, which are astronauts kind of traveling around the moon. I don't know if anyone's heard about this. But the interesting thing that's reported by some astronauts when they get above the atmosphere is that particles actually might be interacting inside their eyelids. And so they report seeing bright flashes of light and when they close their eyes. And one idea on what's causing this is that it might be cosmic rays. And so understanding cosmic rays is actually really important for what we call space health and the kind of prospects of traveling to kind of other systems, because we lose that protection of our atmosphere to this radiation that's kind of all around us. So it's not just important for astronomy, it's actually important for interstellar travel. So it is a matter of mass, but it's also a matter of position, and it's a matter of how they're made. So the way that diagnostically we see whether something's a microquasar or a quasar is it is just a matter of the mass of that black hole. But the question of how you form a massive black hole at the center of a galaxy that are hundreds of thousands of times kind of more massive than the black holes that you get from stars collapsing is a really complicated question. So even though it seems like these two are just black holes, these two black holes are very, very different stories and different histories of what made them. It seems like our picture of what forms microquasars is actually pretty solid. Stars die, they leave black holes. We've seen kind of some of these processes before, and then these little systems will drift around in space until they pick up a star and start ripping stuff apart. But with the massive black holes that we see at the center of the Milky Way, that we see in the center of other galaxies, which are ripping apart material, those kind of questions of how those form is still a question of hot debate.
All right, let's give one more round of applause. We use it for fun. And so I have a random number generator, so I'm just going to read it out. If I get yours, say it really loudly, because I only have 4 things, so don't let me say 5 by mistake. All right. E14, D7, E14, got it, okay. B7, okay. F8, F8, all right, we're at 3, B15, N4, K14. All right. I said K14. All right. Was that? Okay, we'll keep going. L6, K5. All right, L6. All right. Thank you all so much for coming. We hope to see you in May.
Powers of 10, right? So the number of particles that we have at low energies goes like 10 to the minus 1. So it's like this number, right? 0.1, right? And then the other number for that is, you know, all the way up to 19 and then 0, 1, right? And so that plot is showing us, when we look at that, this is basically, you can think of this as like the number of particles, and this is the energy. And so high energy particles are much more common, low energy particles, sorry, much more common, and the high energy particles are much, much, much more rare. Yes. So it's very easy to make something that's low energy. You can basically spit it out no matter what happens. But to get to the highest energy